So last time we finished here, we suggested that in science, often what we want to know is the probability of a theory, and in scientific reasoning, often what we want to do is update the probability we assign to the theory based on some observation. So we want to know the probability of the theory given an observation. And we suggested that this thing will be at least partly a function of these three things. That is, if you want to know the probability of a theory given an observation, to help you know that, you can use the probability of the observation given the theory, which is how strongly the theory predicts the evidence, the probability of the theory independent of the observation, which is the prior probability of the theory, and how probable the observation is. Okay? So why are each of these things important? That is, why do these things affect this one? Well, we'll start with kind of a simple description. And that description is meant to sort of get your intuitions pumping, and then we'll look at some examples. So first, making the probability of an observation given a theory higher should make the probability of a theory given an observation higher, all of the things being equal. To put it another way, a theory should score more points for when an observation is made if it strongly predicts that observation than if it only weakly predicts that observation. So that makes sense, because the more strongly a theory predicts an observation, the more points the theory should score when you make it. I think an example I used in class is this. Suppose that I have a model of how the weather works, let that be my theory, and my model predicts that there's a 90% chance that it's going to rain tomorrow at 3 p.m., and then it rains tomorrow at 3 p.m. Seems like my theory should score a fair amount of points for making that prediction, all of the things being equal, because it really strongly predicted that it was going to rain. In contrast, if a different model of the weather, a different theory, says there's a 10% chance it will rain tomorrow at 3 p.m., then when I observe that it rains tomorrow at 3 p.m., my theory should score some points because it sort of predicted that observation, but it was a pretty weak prediction. It didn't really say with confidence that it was going to rain, so it shouldn't score as many points. So the more strongly your theory predicts an observation, that is, the higher this number, the higher the probability of the observation given the theory, the more points the theory should score when the observation is made. Next, the prior probability of the theory. Well, making that higher should make this higher. That is, making the prior probability of the theory higher should make the probability of the theory given the observation higher. And one way to see this is, all that's saying is you shouldn't ignore old evidence just because you have new evidence. So your old evidence is what determined the probability of the theory independent of that observation. Now you get some new evidence, the new observation, and you want to figure out how probable is your theory given that new observation. Well, you shouldn't throw all the old evidence out the window, and that's what you used to establish this. So by incorporating this, you're accounting for the old evidence as well as the new. Finally, the probability of the observation, making that lower will make the probability of the theory given the observation higher. So why would it happen in that direction? Well, the basic idea is this, that a theory should score more points for predicting something that's surprising, that is, for an observation that's very improbable, than it should score for predicting something that's unsurprising, that is, an observation that's very probable. And the example I gave in class was this: if my theory predicts that the next mammal who walks through the door will be human, and the next mammal that walks through the door is indeed human, maybe my theory should score some points, but you shouldn't be like, man, I'm so impressed by your theory, because it wasn't a very interesting or surprising prediction. But if my theory predicts that the next mammal that walks through the door will be a gorilla, and then the next mammal that walks through the door is indeed a gorilla, you should be very impressed by my theory, because that was very surprising. Nobody expected a gorilla to be coming next to the door except for me. Okay, so let's look at each of these elements. First, theory predicts observation. Suppose that 60 of 100 people who have the flu have a fever, and that only 30 of 100 people who have COVID have a fever. Since 60 out of 100 people who have the flu have a fever, the probability that I have a fever given that I have the flu is 60%. Since the theory that I have a flu predicts that so we could say the theory that I have flu predicts that I have fever with 60% accuracy. Since 30 of 100 people with COVID have a fever, the probability that I have a fever given that I have COVID is 30%. So the theory that I have COVID predicts that I have a fever with 30% accuracy. So the theory that I have the flu predicts my fever more strongly than the theory that I have COVID does. So if all else is equal, we should say, upon observing fever, that I'm more likely to have flu than I am to have COVID. Now, all else might not be equal, so that's why this point scoring metaphor is useful. When deciding what to believe after observing that I have a fever, the theory that I have a flu should score more points for predicting the fever than should the theory that I have COVID, because the theory that I have flu is a stronger predictor. It's like that weather model that said 90% chance of rain tomorrow at 3, versus the theory that I have COVID is more like that weaker weather model that said there's a 10% chance that it will rain tomorrow at 3. Okay. So that's this thing, the likelihood, making the probability of the observation given the theory higher should make the probability of the theory given the observation higher. What about this thing, the prior probability of the theory? Well, that's the starting point. And suppose that one person in the world has COVID and 3 billion people have the flu. Since only one person has COVID, the probability that I have COVID, just no other evidence, is 1 in 8 billion. Since 3 billion people have the flu, the probability that I have the flu, given no other evidence, is 3 out of 8. So when deciding what to believe, the theory that I have flu should have just a much higher starting point. Correspondingly, it should take a lot of evidence to move me off the theory that I have flu, right? Off the theory that I have COVID. It should take a lot of evidence to get me to believe that I have COVID, right? If I start out and I'm like, only 1 in 8 billion has it, it's really improbable that I have it. So whatever my symptoms, I'm like, I probably don't have it. I should need just tons of evidence to get me to believe I have it. Whereas with the flu, if 3 out of 8 people have it, look, it shouldn't take all that much evidence because it's already pretty likely that I have it even before any evidence. So give me some evidence, it should get me over the hump, and I should start thinking there's a good chance I have the flu. Okay, so that's the prior probability of the theory. You can also think of the prior probability of the theory in relation to the Ganzfeld experiment that we talked about. So remember, the Ganzfeld experiment found that slightly more that people on average get slightly more than a quarter of the guesses right in the situation where they're guessing what the person in another room is seeing. And that, someone might think suggests that there's a little bit of ESP because the probability that you get the observation, given the theory that people have ESP, is going to be higher than the probability that you get the observation given the theory that people don't have ESP. To put it another way, the ESP theory predicts that you get greater than a quarter right on average, better than the theory that people don't have ESP predicts that result. And still, we should assign a low probability to, the theory that people have ESP given that observation. Why? Because the prior probability for the theory that people have ESP was so low. It just doesn't fit well with other things we think. Okay, finally, the probability of the observation, making that lower should make the probability of the theory given the observation higher. And to see this, suppose 30 of 100 people who have COVID have fever and 10 of 100 people who have COVID lose their sense of smell. So the theory that I have COVID predicts that I have a fever with 30% accuracy, while the theory that I have COVID predicts that I lose my sense of smell with only 10% accuracy. Nonetheless, the theory that I have COVID predicts my fever more strongly than the theory that it predicts my loss of sense of smell. Nonetheless, when deciding what to believe, the theory that I have COVID should sort of score more points for predicting the observation that I lost my sense of smell, if that observation is made, than it should for predicting my fever, if that observation is made. Why? Well, it's roughly because the observation of losing sense of smell is very surprising. There are very few things that cause the loss of sense of smell. It's a very unusual thing to have happen. Whereas the observation that I have fever is very unsurprising. There's many things that cause fever, and there's a lot of fever around, so it's not that surprising. So lots of people have fevers for lots of other reasons. So when you observe fever, you're not going to be like, man, that's almost certainly COVID. But very few people lose a sense of smell for other reasons. So when you observe loss of sense of smell, you'd be like, probably COVID. Okay? So hopefully that gives you a sense of why we need each of these three elements. The question now is how to put them together. And we already said that making the probability of the observation given the theory higher should make the probability of the theory given the observation higher. So mathematically, if we're trying to get this thing to go up as this one goes up, we want them on the same level here. The probability of the theory given the observation should go up as the probability of the theory goes up. So again, we should keep this on the same level here. And the probability of the theory given the observation should go up as the probability of the observation goes down. So we need to divide by the probability of the observation to make this go up as this goes down. And we multiply those, and we get Bayes' theorem, which is Bayesian confirmation theory. It tells us to put these elements together in this way. Now, as I mentioned in class, this is not universally accepted. This is, I take it, the dominant view in philosophy of science these days about theory confirmation and disconfirmation. But it's not universally accepted. And one reason, there's a few, but one reason why it's not universally accepted is that although everybody agrees that as this goes down, this goes up, and as these two go up, this goes up, not everybody agrees that this is a complete picture. So maybe there are other factors that also influence this. That is, other factors that also influence the probability you should assign to a theory given an observation, aside from these three. But this formula only identifies these three. It says these three, this thing here, the probability of the theory given the observation, is just a function of these three. So if there's other factors, then this is incomplete. Like maybe the simplicity of a theory, maybe the simpler a theory is, the higher a probability you should assign to it given an observation. And maybe simplicity isn't encoded over here. Or maybe simplicity is encoded. Maybe it plays a role in determining the prior probability of the theory. What I want you to see, what I want you to know is just that this isn't universally accepted, but it is the dominant view. And it is pretty much universally accepted that these three things are related to this. It's just maybe more is needed. Okay, so we'll stop this video there, and in the next video, we'll look at an example and then compare that example to kind of a more realistic case.